Last time we started section 2.3 and we introduced several new set operations. We talked about intersection being the crossing point or the place where things meet, what they have in common. We talked about the set union being the joining of two different sets sort of all in one big melting pot, like America, or like a wedding is what I kept talking about. We talked about relative difference. We haven't done a lot with that. We did talk about it and how it's taking the part they have in common and removing that part from the original set you're talking about. We did Cartesian products as well over here, where we paired things up in some sort of a pairing, and we counted the number of pairings that has happened when we did that, and this is just two at a time, and so we created these ordered pairs, and we had started looking at Venn diagrams. And I introduced this idea of labeling the different regions in the Venn diagrams with numbers to distinguish them from one another so that we're able to do the shading. And I believe we have one more of those to take a look at today. So I did these examples earlier on. The first one because it only had two sets, so I wanted to develop the idea of what we would do with three sets. And then when I did the three sets here, I wanted them to be the three simplest options, right? There's no complements or anything going on. We just have the union and intersection symbols. And then this one kind of combines all of those ideas together. So I have some complements, I have three sets, I happen to only have intersections on this one, which is okay, but we're still going to approach it in very much the same way. So to start with, draw yourself a Venn diagram, rectangle, and inside of it, create your three circles that overlap. And then we're going to label first the sections of our, not the sections, but the circles themselves. So like A, B, C, and the universal set U. And then we're going to label the regions. And again, it's nothing that you have to label in this way. I'd appreciate it if you do, because it makes it easier to make sure we don't make any mistakes on grading if everybody's numbering the same way. But it does seem very natural to just number straight across, top to bottom, left to right. So I have 1, 2, 3, 4, 5, 6, 7 in the bottom and C, and 8 out here in the rectangle itself. So if you'll remember what we did last time is we started on the inside of the set of parentheses with the individual components that are there. So our individual components here are A and B complement. So we're not interested in simply writing down everything in A, everything in B, everything in C, if A, B, and C happen to not be what we're using, but we're using complements instead. We really only want to write down the components that we have, and we want to do it piece by piece. So we're starting with A and B complement because they're inside the parentheses. So what regions are inside of circle A? What numbers? 1, 2, 4, and 5. Is everybody good with those and knows where they came from? You can visually see the pieces. Great. B complement means everything not in B. So what regions of this graph are not inside of circle B? Wonderful. And then those are the individual components inside the parentheses. Now we join them with the operation inside the parentheses. And the operation is in fact an intersection. So using what we did last time, intersections, is it what they have in common, or is it mushing them all together? What they have in common. And what numbers do these two sets have in common? 1 and 4, right. So my intersection here is 1 and 4. Now I've done everything inside of the parentheses, it's all complete. So we move to the outside of the parentheses and we pick up the third set. And the third set here is actually C complement. So again, not in C. So what numbers are not in C? 1, 2, 3, and 8. Yeah, don't forget 8. Sometimes people forget that 8 hanging out there. It's also included. And then I'm going to join these two sets, namely the set A intersect B complement. That's one set. And I'm going to join it with an intersection with C complement. You guys told me before, intersections are what they have in common. So what do these two sets have in common? I think it's just one. You were probably on the line before. Yeah, the two that are kind of sandwiched in the middle there. Just number 1, right? So that's the work portion of what we're doing. And then we go back to our diagram to shade. So the only region that's included in my shading this time is region 1. Okay, does that make sense? Okay. The next thing we're going to do is shift gears. We're still going to be doing Venn diagrams, but we're no longer interested in the regions as just these sort of arbitrary areas. They're going to represent certain quantities. In particular, what we're looking at on the next example is the number of items that occur in a particular area of the graph. Okay? So this problem actually sets us up so that we can think about it in a context situation on the next two after this. But this is just giving us some values to play around with so we can see how the process works. So if you take a look at your original graph with the 3 circles, okay, so start by drawing that again. And labeling them, of course, in the same way as before, A, B, C, and the universal set. So our numbers here now are not representing just sections of the area like they did on the last 3 problems. The numbers we're going to be putting in are going to be representing sort of like categories of things. So there's a category in the location where we put the number 1 before, and there's certain elements or items or people or books or telephone numbers or whatever that are sort of in that category. Okay? So what you might think of this as is something like if I took my my phone list in my phone, right, all the phone numbers that I have, and we took my husband's phone list, and he was circle B, and we took my son's phone list, and he was circle C. Some of those phone numbers we all have in common, right? They're in all 3 of our phones, and some of them aren't. Some of my friends have absolutely no reason to be in my husband's or my son's phone book, right? So that's what we're looking at. We're looking at these overlapping pieces where we have things in common and places where we have nothing in common. I'm the only one who has Sarah Marsh in my phone, right? Something like that. So that's what we're going to be going and doing on this. But right now what we're writing in each of these areas is simply the number of people, we'll say it in terms of my description, that sort of are in that category. The problem is that if you take a look at the intro information, that first line, this number of items or elements in set A means anywhere inside of this circle. If you count them up pretty quickly, there's 4 different regions in that circle, right? Parts of them overlap with B, parts of them overlap with C, parts of them are A only, but there's 4 different regions, and if I want to put the number 24 somewhere in here, I have quite a few ways I could do that. I could put the 24 in each one of the 4 regions. I could break it apart into 12 and 12, or maybe I have 6 and 6 and 4 and, whatever's left, 8. I mean, I can break it apart in lots of different ways. So starting out with the number of items in set A is not a good place to start because I have too many places that I could put different numbers, and it would actually work. So that sort of is the same argument for why any of these 3 don't work, right, with set B or set C in the same way. Now, if you go to the next line, the number of items in A intersect B, we've narrowed it down some. This is the region right here where A intersects B. But there's still 2 areas here, right? So I could put 10 and 0, I could put 5 and 5, I could put 7 and 3 or 3 and 7. I still have quite a few different ways that I could arrange this. How many of you have ever done a Sudoku puzzle? You know what I'm talking about? It's kind of like that. You don't want to fill in the one where you have like 3 different numbers that it could be, right? I mean, like that makes things harder. You're looking for very narrowly the one that absolutely has to be a 4, and that's where you put the 4. We're doing that. So this second line right here, with all these intersections of 2 sets, all have the same sort of problem. I have 2 different regions where they intersect. But if you move down to this piece right here, it's a very nice piece. Because as it says that all 3 of the sets have to intersect. And that only happens in the very dead center of this picture, right? Yeah, that only happens there. So that number 6, actually I'll go with this and highlight it like I did. That number 6 is right here in the center. Because there's only one place that it identifies, as opposed to having 2 or 4 or more. The cool thing is, once I did that piece, if I move up one line to where I have the two sets intersecting, I can actually finish that line now as well. So let me show you. This piece right here, right here, where it says circle A intersects circle B, well, that's still these two pieces, right? They still have to be 10 items in there, but I already have 6 in the bottom corner. So how many is going to be up the top? 4. I don't really have any choices any longer, which is kind of what I was hoping for, right? I don't want to have to make a choice. I want my choice to be made for me. It has to be a 4. And I can keep going with that. The next one is 8 for B intersects C. So B intersects C is right here. So how many has to be in that outer part of those two pieces? 2. So there's a 2 right here. And then the last one with A intersects C is 15. That piece is right here, right? So I need a 9. 9 and 6 to make my 15. Okay, so we're working from the inside out. Now let me make one word of caution. They don't always start dead center. Sometimes they say things like, it's in the set A only. Well, if it's in set A only, it's the outer part of A, right? That might be the way that they identify one specific location. Or they might in some way, shape, or form tell you that, for instance, A and B overlap, but they never overlap with circle C. Well, if they never overlap with C, it tells you 0's in the middle, and you can keep working through pieces, all right? So it doesn't always start with the very center piece. It's a nice place, but it's not always the place. Now, if we move up one more line to the top line, 24 in circle A. Well, take a look at circle A. It previously had 4 unknown values, but I know 3 of them now, don't I? 9, 6, and 4. How many of them are already accounted for? 19. So if there's supposed to be 24 inside of circle A, how many are unaccounted for? Just 5. So those are in essence, the 5 numbers that are in my phone and in none of my family's phone number, okay? That would be what we were saying. We can go over to circle B and we can do the same thing. Circle B is supposed to also happen to have 24. And inside of circle B right now, how many are accounted for? 12. Yeah? Yeah, so that leaves me with 12 more outside in the circle B only part. And if I do the same thing inside of circle C, it's supposed to be 26. How many are in it already? 17. So how many remain? 9. There's only one piece of information that I didn't highlight yet. It's the last piece. It's just where it happens to occur, the number of items in the entire thing. That's not the number of items in the outer part. That's not what that's describing. It's describing everything inside the rectangle. In other words, if I merged my phone book and my husband's phone book and my son's phone book into one massive phone book, it'd be all the numbers in that phone book or all the people in that phone directory or whatever you want to call it, okay? So the set U is everything in the rectangle. There's already 7 different numbers. They're not all different from one another, but there's 7 numbers inside of my rectangle. So how many, 5, 4, 12, 9, 6, 2, and 9, how many are already there? 47 is what I think I remember it being 2. Did anybody else double check it? It was just AK. Did you add fast in your head? 47. I got a couple people saying 47. So if there's 47 in all those circle pieces already, how many are in the outer part of the rectangle? 3. Yeah. Whoops. Get the right pen. 3. So this sort of idea of piecing together based on criteria actually is a really good problem-solving strategy using Venn diagrams when we have language and overlapping descriptions. So take a look at example number 4 and you'll see what I mean. Joe Long works on albums for musicians. Last year he worked on 12 projects. He wrote and produced 2. He wrote a total of 5 and he produced a total of 7. And then we've got a bunch of questions after it. Now notice there's nothing on here that says draw a Venn diagram. It doesn't say that. But Venn diagram works really, really well to make these questions super easy to answer. Okay? So that's what we're going to do is we're going to, in fact, draw a Venn diagram. Now, we have to decide how many circles are in our diagram based on the description that we were given about Joe. What are the different categories? AK says 2. What do you think they are, AK?
He wrote and produced, and then the middle one he wrote and produced.
Okay, so that sounds good to me. We don't want more circles than we have to have. I mean, definitely don't. So we have one circle that's going to be the wrote circle, where he wrote the songs. And we're going to have one circle that is the produced circle. And you're exactly right. The overlapping part in the middle is where he wrote and produced something. And then we're going to go ahead and label U for the universal set on the outside. We could label it A and B, but we somehow have to indicate which one is the wrote one and which is the produced, so writing the descriptions in there is a good way to do that anyway. So taking a look back over at the pieces of information, there are several pieces. There's one that says worked on 12, there's one that said wrote and produced 2, one that says wrote 5, and one that says produced 7. Which piece is the piece that's most helpful to start with? Yeah, the wrote and produced 2. So in our diagram, where does that 2 go? In the middle. Exactly. Everybody good? Okay, what's the next piece of information you'd like to work with? Wrote 5. Okay, so if we move to the wrote 5 now, where am I going to put my 5?
Well, it wouldn't be a 5 because you already have 2, but it would be in the row circle still.
Good. I'm so glad you corrected how I said it. I was trying to lead you astray. You caught me. Yeah, there's not a 5 that I put anywhere, right? Because the entire wrote circle needs to be 5, which means I only need 3 more in that piece of the circle to add up to 5. Wonderful. And then if I've done that piece, probably the produced 7 would be our next spot. So what number will I put and where? This one will actually be a 5, yeah, in the produced part, because 5 plus 2 is my 7. What am I going to do on the outside part of U? 2. Where did you get 2 from? Yeah, okay. So I have 12, and I'm subtracting. So I'm taking my 12, and I'm taking away the 5, the 2, and the 3. So that leaves me, like you said, with 2 on the outside. Okay, so this is the work that supports answering the questions that I'm about to now answer. So if you make a mistake on this, but then your answer matches your diagram, then you would be getting credit, like think about from a testing perspective, credit for understanding how to interpret your diagram, but maybe having to rework or rethink about parts of your diagram and how you created it. So there's 2 separate aspects of this. So thinking about this diagram, in fact, I think I can, whoops, let me try that again. There's a little bitty one right there. All right, so thinking about this diagram, we're going to answer the questions that were asked below. The first one says, how many projects did Joe write but not produce? 3. How many projects did he produce but not write? 5. And how many projects did he neither write nor produce? 2. So he did something else on those 2, right? Okay, so answering the questions should be fairly straightforward from your diagram, which is kind of the point in creating the diagram to begin with. All right, we have one more example, I believe. Or maybe 2 more. All right, one more Venn diagrams, that was what I was thinking. So this is an example about some songs. So a youth group was asked questions regarding the songs they'd learned as children. Upon surveying the 34 youth, the following were obtained. 15 had learned Jesus Loves Me. 19 had learned the Bible. 28 had learned This Little Light of Mine. 13 had learned Jesus loves me and this little light of mine. 15, Jesus loves me and the BIBLE. 14, the BIBLE and this little light of mine. And 13 had learned all three. So, first thing I'm going to do is to create a Venn diagram with how many circles? 3. What will my circles be? All right. So I'll abbreviate a little bit. So this one's Jesus loves me. I'll just call it Jesus. This one's the BIBLE. So I'll just write BIBLE. And the last one is this little light of mine, and I'll just write light. And this is all inside of circle U, or universal set U. All right. Where in all of this am I going to start? The 13 at all three. You're right, Elizabeth. Where's the 13 going to go on my picture? Yeah, in the middle. Okay, so the 13 is the people who've learned all three of those songs. What's next? So I think Brooklyn's telling me I can just go up from the bottom. Is that what I heard you saying?
Yeah.
Sure. So we can do all the ones with the 2 songs. That's what Brooke over here said. And I think you guys are both on the same track. So any of these next 3 above where we are fine for me to go to next, right? So I'll just go from the bottom up, like Brooklyn suggested, with this 14 next. So this is 14 is BIBLE and this little light of mine. So the BIBLE and this little light of mine is this piece over here, right? And it's supposed to be a total of 14. So how many more do I need? 1. So 1 goes here. The next one was that 15 had learned Jesus loves me in the BIBLE. So Jesus loves me in the BIBLE are here. And it's supposed to be 15. So I need 2 in this top cross section. And the third one where it combines 2 pieces is 13 had learned Jesus loves me in this little light of mine. So that's this piece. So I need a 0. And 0 is perfectly acceptable. There are things that are not. We can't put negatives in this picture. It doesn't make any sense. Can't put fractions or decimals, but we can definitely put the number 0. All right, what would you like to fill in next? Which piece of information? Yeah, we could keep going up, right? These last 3 actually are all very similar in the sense that they still find the same portion of the graph in a different circle, but the same portion. So if we want to just keep working our way up, we can go to the 28. 28 is for this little light of mine. So this circle is this little light of mine, and it needs to be a total of 28. How many are in it already? 14. So how many am I missing? 14. Okay. The next one is 19 with the BIBLE. Right? So that's this circle. Needs to be 19. How many are there already? 16. So how many are missing? 3. And our last listed item is the 15 had learned Jesus loves me. So here's my Jesus loves me. So there's 0. Okay. I still need the outer part of the rectangle, right? So what over here have I not done? The 34 youth. There's supposed to be 34 people answering these questions. So how many are counted for right now? 33. So I need how many more? 1 on the outside. Okay, so this is our diagram. Let me make it smaller so that we have it as a reference point on my previous screen. Okay, so using this as a reference point, how many children learned exactly 1 song? Okay, so where did you get your numbers from to give me 17?
I added all the ones that just like 1 song.
Okay, so all of them that are in like 1 song value. So we would be at the 0, the 3, and the 14. Are those the 3 you were mentioning? Right. So when you're writing these down, it would be helpful to me, and it would be helpful to you, in case you do make a mistake, for you to write down the numbers that you're adding up. So here you're adding up 0 plus 14 plus 3 in some order. I don't care. and that's what's giving me the 17. So it's not always true that every number is unique within your diagram, but I can at least try and figure out if you've made a mistake, maybe why it's happening, and to help you out to think about why it doesn't work the way that you maybe anticipated it was. I'm sorry, I wrote that on the wrong line. Or look at me like I'm crazy. How about that? Okay, cool. How about at least two of these songs? What numbers are in the at least two of these songs categories? 2, 13, 1 and 0, right? So the 2 is definitely in 2 circles. The 1 is in 2 circles, and the 0 is in 2 circles. Why am I including the number 13? Yeah, because it says at least 2, which means it could be 2 or 3 in our case, right? That's why the 13 is getting included. If it said exactly 2, or it just said 2, right? We'd use the word exactly. If it's exactly 2, then you wouldn't get to include the 13. Okay, so if we add all these together, what are we going to end up with? We have 16. How about none of these songs? Well, and that poor child. Somebody didn't take him to Sunday school. I need to find him and bring him along. And then this little light of mine only. The 14, right? It's in the outer region. So some of them we have, additions of components of our diagram, and some of them are just one component of our diagram. It just depends. All right, last question for today. Is the Cartesian product commutative? Why or why not? So if you remember, commutative means you can change orders of things. For example, multiplication, which we'll get to more of this later, but multiplication is commutative. 5 times 3 is 3 times 5. So is the Cartesian product commutative? So remember, Cartesian product is the ones where we did the ordering of pairs. Does A cross B is equal to B cross A?
Yes.
Do you think? Let's go back to our example where I had ones written out so we can look at it, because it'll be easier to think about it from there. Oh my goodness, where'd it go? How about here? All right, so A cross B is what I wrote out in the middle of this screen. Let's actually write out what B cross A is. I'll shrink this so we have space. All right, so this is B cross A. So B cross A would mean that I take an item in B, so like 1, and I pair it with an item in A, so this would be like 1x. Or I do 1y or 1z. Or I can do an item from B that's 2, so 2x and 2y and 2z. So I still end up with 6 elements, but are they the same elements? No, they're not. So you can see there's sort of a natural pairing, right, of the ones that have the same items within their pair. Like 1x and x1 somehow seem to have this natural correspondence to one another. But think about this from like a graphing perspective. Is 1, 3 and 3, 1 the same point on the line or the curve or on the shape or whatever? No, it's not. So this doesn't work. It produces equivalent sets, right? Equivalent means same number of items, but it does not produce equal sets. So over here, we would have to say no. And the reason is because in general, and we'll use some numbers, 1, 3 is not the same as the ordered pair 3, 1. Right? Obviously the ordered pair 2, 2 would work because you flip them and it's still 2, 2. But most of the ordered pair components aren't going to do that. They're going to be different. Any questions on that? So that's very interesting because intersections and unions, they were commutative, but Cartesian products are not.